Thank you. So our next talk is boosting performance of HPC applications with MVAPICH2. And the speakers are going to be Dr. Hari Subramoni and Nat Shineman. Dr. Hari Subramoni was a research scientist in the Department of Computer Science and Engineering, and he's now an assistant professor. His current research interests include high-performance interconnects and protocols, parallel computer architecture, network-based computing, exascale computing, network topology-aware computing, and the list goes on and on. He has published over 100 papers in international journals and conferences related to these research areas. And Nat Shineman is a software engineer in the Department of Computer Science and Engineering at OSU. His current development work includes high-performance interconnects, parallel computing, scalable startup mechanisms, performance analysis, and debugging of the MVAPICH2 library. Over to you guys.
Thanks, Amir. So before we start, Nat has a couple of announcements to make regarding like the logistics of how we would like to do the hybrid conference. Nat?
Yes, so sorry about the delay here, but we had to troubleshoot some of the table mics for a sec. So if everyone attending in person could make sure that when you're asking questions, you hit that little button on your table mic, you should see a green light pop on. But right now, if you could check your mic and make sure that that green light is not on, it turns out those are a toggle and not a hold. So you will toggle that on, and then you need to toggle it off. Otherwise, we get that really horrible reverb we were getting earlier. So thank you. And if there's an empty desk near you, please double check that those are off as well.
Sure. Hi, guys. I'm really glad to see all of you in person. So that makes a lot of difference. So we are holding this conference in person after 2 years. Very glad that you're all here. So this tutorial is going to be a high-level overview of the features in MVAPICH2 and what we, in particular, what we have been able to do in the last 1 year. So obviously, the project has been around for like over 2 decades. So we have been doing a lot. So this would just focus on what we did recently, what are the new things there, what are the benefits because of that, who are we collaborating with, things like that, okay? We are also trying to have, let's say, speed up some of these presentations. So I know that several of you had signed on for the State of Ohio Computer Center tour in the evening today. So in order to have enough time for that, we are trying to prepone all of the events by around 10 to 15 minutes. So we'll try to finish this session by around 2:45 or 2:50. We'll have the break from 2:50 to maybe 3:10 or 3:10 or something like that, so that we can take back some time, okay? So having said that, basically I talk and he does all the work, all right? So this time around, we caught him and said that, hey, you also talk. So we'll give him more work, right, Nat?
Yes.
So, okay. So we've been around for quite a bit, right? So all of you guys know that we are used almost all around the world. We've been around for like 21 years. And I've been lucky enough to be part of this project for the last 15 of those 21 years, okay? So we are used by a lot of organizations around the world. So for more details, please visit our website. I will not bore you anymore with that. So this is a broad architecture of the Embapage software stack. So broadly, if you take a look at it, any communication middleware has a lot of fundamental operations that you would like to perform, like point-to-point, collective, so on and so forth, right? In order to ensure that all of these operations have good performance, you need to have it designed for the particular hardware architecture underneath. It could be an interconnect, it could be the GPU, a CPU, so whatever it is. So that is what we do in short. We try to make sure that we can take multiple programming models, optimize the various primitives offered by those programming models for modern interconnect GPU and CPU architectures. So we are basically a research institution. So a lot of people have this hesitation. Hey, you guys are a university. What do you know about software development? How do I know that the code that you run will not crash my entire system? So to make sure that that doesn't happen, and we don't bring down entire supercomputers of 8,000 odd nodes, we have a very rigorous Q&A procedure, and like all of the students and staff members sitting here are part of that. So we make sure that we put the software through its paces through a lot of rigorous testing, Q&A, and we spend close to about 18 to 20,000 core hours per each commit to make sure that things are stable. And we take it through like the standard software development process of alpha, beta, RC1 testing before it is released to the wide open world. This is a snapshot of how we do testing. We have developed all of these testing harnesses in-house to monitor testing, to progress testing, to make sure that things are passing. We have like a good like percentage of things that are passing. I don't know if you guys have gone through the MVAPICH user guide. Can I get a show of hands? How many of you have actually looked at the MVAPICH user guide? Adam, I know you have. So, okay, wow. Okay, a fair number. I'm quite surprised. No wonder you're here at MUG. So we have about 600 different parameters, right? So how do you make sure that all of these parameters gets triggered, how all the code paths that these parameters protect get used? So that is why we have all of these advanced testing frameworks where every single path as much as possible is tested. And we have two kinds of validation. One is functionality, the other is performance. So we need to make sure that release upon release, we don't degrade in performance, and that's where we have in-house performance regression scripts. I was just talking to some of the new students saying that, hey, go ahead and run these things to make sure that things work fine. So these are the kind of things that we do day in and day out to make sure that release upon release, we kind of increase the performance and not go the other way. We are also support various cloud platforms. So we have been supporting traditional HPC centers for over 15 years. Over the last 5 years or so, a lot of cloud vendors have come up with high performance computing offerings are called the HPC clouds. So you have Microsoft Azure, Amazon, AWS, Oracle's like OCI Shape, so on and so forth. So we support optimized solutions for all of those. And we also support SPAC based. So I believe we have a SPAC developer here. Oh, there he is sitting. So we'll be talking about how we integrate with SPAC. So both are open source as well as the closed source binary only packages are available through SPAC. So if you are a SPAC house, then you can use SPAC to install it. So this is the workflow as to how we deploy our various solutions through SPAC. And that is from our end. From your end, all you will have to do is something as simple as this. If you want to install the open source version or any of the closed source versions. So we have several mirrors hosted on our website. So this is our broad plan. So where we want to be in the next 5 to 10 years. So we want to have like good scalability for like hundreds of thousands to millions of processes. Scalable collective communication, point-to-point communication, support for GPUs and accelerators. And you will see that in tomorrow's talk, Dr. Panda is going to kind of allude to how we are planning to bring all of these under one stack. So in the past, we have had several different distributions that have been forced on us by the way the community evolved. So we are planning to bring all of these under one roof going forward, and Dr. Panda will be talking a bit about that tomorrow. So we'll be talking about various software products or families that we support. We'll start with the open source Embapage product. Then we'll talk about MVAPICH2X, MVAPICH2 GDR, and some about the OSU micro benchmark suite and kind of wrap up. So as I said, now we are trying to give Nat more work. So I'll invite Nat to talk about the open source Embapage side and what Nat has been doing to lead that effort over the last 1 year. Nat?
Thanks, Hari.
Just one more thing. Guys, it's really, really boring if you just sit and have these blank 10,000-mile stares. So ask questions. That makes things more interesting. I know, Adam, I can count on you for questions. But others, yeah, please do ask questions. Thanks.
Yeah, so feel free to just jump in and ask questions because most of the things I'm going to cover are stuff that we do get a lot of questions about on Discuss as it is. So first of all, we recently released our 2.3.7 version of the open source MVAPICH2 project. So this was a little bit ago on March 2nd. So this is mostly a stability and bug fix release. We added a lot of stability patches through that testing framework to really boost our reliability over the 2.3.6 version. But we also did have some pretty major new features, including support for the Rockport switchless networking, which is a next generation networking system. And that we have automatic architecture detection as well as optimized point-to-point performance on those networks. We also added support for the Cray Slingshot 10 interconnect, which is powering a lot of the next-gen systems. They're actually moving a lot of that to Slingshot 11. We'll touch on that in a little bit. And then we also added some more support for the Mellanox Sharp that had been introduced a few releases prior. So we added support for the Scatter and Scatter V collective, as well as non-blocking collectives, IL-reduce, iBarrier, IBcast, and iReduce. And then we did a bunch more tuning because there are more and more systems coming out, and we tried to have the best possible performance out of the box for as many systems as possible so that as end users, you can just run it and see great performance without having to do too much on your end. So we're going to touch on a couple features of the MVAPICH2 library, starting with the process mapping for point-to-point and intranode performance, and then covering some collectives. So process mapping is one of those things that is really important to application developers because you can have a great MPI library, but if your process mappings aren't conducive to what you're doing, you're going to not see as large of benefits as you could be getting. So we support a number of preset binding policies that are really easy to just assign to your process. And then we also support a user-defined binding. So, and again, this is something we get questions about a lot on our mailing list, saying like, hey, I've done all this stuff to optimize my performance, but it's not coming out how I would like. And one of the first things we typically look at is, how are your CPU bindings happening? So our default binding policy is the bunch binding. So this is going to basically keep all of your processes close together, and it's really good for intranode performance. So basically, you're going to see on consecutive cores on one socket, you'll get all of your processes mapped together. So you can kind of see that in the diagram here. And this is great for that intranode performance because they're going to be as close as physically possible on one processor. We can also do that, so that's at the core level. We can also do that at the socket level, which is going to let them kind of float around in that socket. And this is great if you're doing some threading or you want a little bit more flexibility there. We also have the scatter option, which is going to allow you to basically alternate. You can see here, rank 0 is going to be on the first socket, rank 1 is going to be on the next socket, and then we'll go back. So we'll actually alternate between the sockets available to you. And this is great if you're doing something, say, with resources that are on different sockets, right? You wouldn't want to, if you have two network adapters, one on each socket, you're going to get better internode performance if you can keep those balanced, right? So that if you have a multi-Pneuma system, you're not overloading one of those HCAs by just keeping all your processes on one socket. And again, we can do something similar at the socket level for additional flexibility. Recently, we've introduced a newer hybrid binding policy, and this is great because a lot of applications are moving towards a hybrid approach to parallelism, so using both MPI and something like OpenMP or POSIX threads to do MPI and threading. So this actually ends up being the default on many systems based on architecture detection. And this will allow you to set this MV2 threads per process, and you can assign both one of those more traditional binding policies, like the bunch or scatter, but then actually allocate several cores to a single process, which will allow it to map each of its child threads to the processes. And this will be automatically set if OMP num threads is set in your environment, which is, again, really nice. If you're using OMP, you can just kind of fire and forget, and it'll take care of itself. So we support several different hybrid binding policies, which you can see here, and it's definitely a worthwhile environment variable to kind of mess around with and see what you get best performance with for your application. And we have more details about all of these in our user guide as well. But so here are just a couple examples of the hybrid binding policies. So you can see this is compact. It's going to try to keep all of your threads as close together as possible. And this will be used with hardware thread detection for your specific architecture. This is the linear binding, which looks a lot like the traditional bunch policy, but it is also thread aware. So it's going to, again, in this case, we have 4 threads per process. So you're going to see that rank 0 is actually allocated the first 4 cores on the system, so it can launch all of its hardware threads there. And then finally, we have the Pneuma aware binding, which is one of our newest binding policies. And this is really nice for some of these like newer AMD EPYC, Rome and Milan processors that can have 8 or more Pneumas on a single node. And these will actually stagger your processes throughout the different Pneuma domains, and then again assign the number of cores corresponding to the number of threads you're launching. Yes. So like I said, you can set either OMP num threads, or you can set, we have an MVAPICH2 specific variable if you're using something other than OpenMP. So that will basically, it will tell the library, okay, I'm going to have this many threads launched on each process. And we use HWLock to check the number of hardware threads and the number of cores on each Pneuma domain. And then we allocate those to an individual process and basically tie those processes down to the actual CPU cores. So when they spawn their child threads, they're going to be restricted to those, say 4 cores, and all of your processes are going to be bound to a specific processor. Does that answer your question?
Is SMT and hyperthreading supported with this?
It is supported due to the nature of those being, software threads and not hardware threads. Performance isn't quite as good, but it is supported.
So it sounds like generally you don't want to use that.
Depends on your workload, really. And then we also have user-defined process mapping, so you can actually explicitly set your own process to core mapping, which just gives you additional flexibility. This is one of those things that most users probably won't end up seeing a lot of use for, but is really useful for debugging your application, or if you're trying to get more information about your machine itself, because you can experiment with loading different Pneuma domains, loading a different socket, seeing how that impacts your network adapters, your GPUs, whatever. And so if you're debugging or want to experiment with this, we do support an environment variable, MV2 shows CPU binding. And this is one of those things that is indispensable in debugging performance issues, is to go and check which CPUs are my processes being bound to. And we now have the same support for checking your network adapters with MV2 show HCA binding. And on the GDR version, in our most recent release, we added a show GPU binding, so you can see which GPUs your processes are bound to as well. And again, there's more information on this and optimizing your performance in our user guide. All right, so next we're going to talk about the collective communications in MVAPICH2. So we have, one of the strengths of MVAPICH2 is our custom implementation of the MPI collectives. So we have both blocking and non-blocking collectives implemented in MVAPICH2 237. And we have our conventional flat algorithms, which are much less interesting. And we have our multi-core and aware designs, which are really where we see a lot of benefit, especially in modern systems where you're seeing denser and denser CPUs. So these typically take a 2-stage approach where there's both an internode and an intranode phase. And this allows us to be much more efficient than those flat algorithms that are treating all of those processes the same way. So the internode communication, we have our point-to-point support for various transport protocols. We can use most of the IB verbs. We can use, depending on how MVAPICH2 is built, we can use PSM. And in some of our newer versions, we're adding support for many of these upcoming new network architectures through the OFI and UCX communication libraries. So we have those, but we can also use certain advanced features like hardware multicast, Sharp, and RDMA. And that can handle the internode portion of the collectives, while our intranode can be enhanced by using shared memory, the Linux cross-memory attach, CMA, or limit, depending on how the system is set up and what can provide the best performance. So by splitting those two portions of the collective up, we can achieve much higher performance. And these are mostly on by default, but you can force the MV2 Shineman collectives to ensure that those are on. And so this is just some performance analysis of our hardware multicast with Bcast on the TAC from Terra system. So as you can see, we're able to achieve 2 times speed up on most of these, at most scales by using the hardware multicast. So if your hardware supports it, this is a great way to really enhance performance. And these are all run at 2,000 nodes, which, it's a pretty hefty workload. This is MPI scatter, similar thing. So you can see here, for these small messages, we're able to vastly improve performance at very large scale. And so this can be enabled with the MV2 use MCAS flag. We've also added Sharp support. This was previously added to MVAPICH2X, and we've recently brought it over to the main MVAPICH2 library. So this is a really cool feature that basically has an FPGA on the network adapter and allows it to do in-network compute, which is pretty awesome. So this can really benefit performance. And if you want to know more about that, we actually had a couple talks specifically on Sharp last year at MUG, so you can check our YouTube for those. But here's some performance graphs of blocking collectives with Sharp, with the in-network computing. So as you can see, these were taken with MVAPICH2X. We've recently brought that feature over to the open source library. But as you can see, we're able to get 5 to 9 times performance increases by using that. And again, here's non-blocking collectives. And once again, you can see, we're well over 5 times performance improvements. And this is just some application level analysis with Sharp because, micro benchmarks are great, but they don't actually emulate the application workloads that we really need to improve performance on. So this needs to be enabled at configure time with the enable Sharp flag if your system supports it. And there'll be some checks, and configure will complain loudly if it doesn't find the right headers. And then to enable it at runtime, use MV2 enable Sharp. And again, Bharath did a talk about this at last year's MUG, so I would highly encourage you to check that out if you want to see more details about Sharp in MVAPICH2. Okay, so that's what we have in our release version. This is the part I'm really excited about because my whole thing in the last 2 years I've been here has been to kind of try and push us to the next generation of MVAPICH2. So we recently, about a week ago, released our 3.0 alpha version, which is really trying to move MVAPICH2 into the future. So this is based on MPICH 3.4.3, which is the final version of MPICH to implement the 3.1, the MPI 3.1 standard. So it is the latest base version. And then we've added support for MPICH's new CH4 device with both UCX and OFI as the underlying transport. So we've added all of those enhanced collectives, the CPU binding stuff I just talked about. We've added that on top of MPICH's newer CH4 device. Which is great because we were previously using CH3, and CH4 is a much lighter weight, lower overhead device that's going to really allow us to do a lot of enhancements going forward. So support for the OFI and UCX communication runtime libraries is the biggest feature here. because this allows us to run on a lot of new hardware that we wouldn't be able to support otherwise. So this includes the Cray Slingshot 11 interconnects, which are powering some of the upcoming exascale systems, as well as the Cornelis OPX library that we just heard about earlier, Intel PSM3, and then we can also still support IB verbs over UCX for InfiniBand and Rocky adapters. So these can be configured with the same flags that you'll see with MPICH, with device CH4OFI or UCX, depending on which you want to use. If the configure scripts detect either on your system, they can just build with those. Otherwise, you can pass in specifically a path to one of those libraries, or you can build an embedded version that ships with the tarball. And then we can do runtime selection of providers through environment variables. So that means you can experiment with using different OFI providers based on what's on your system. So all of these support those enhanced two-level collectives that I mentioned earlier. And we're going to be continuing to enhance this alpha version to eventually get to a stable release that will include more features, including our own netmod with enhanced support for different networks outside of those OFI and UCX ones, as well as GPU support and new launchers. So this is just some quick performance graphs of this alpha version, which has been kind of our focus for this first half of the year. So here is, this is actually 237 on Broadcom's Rocky HCAs. And as you can see, we're getting 3.8 microsecond latency for small messages on here. And this was on 2 gigahertz AMD Rome processors. And these are bandwidth numbers on the same. And okay, here are the Slingshot 11 numbers. So these are the new Cray Slingshot 11 interconnects. And as you can see, we're getting 2 microsecond internode latency for point-to-point messages. And this is, again, on an AMD Milan processor. So these are those really dense nodes where those CPU binding policies really come into play.
So it is kind of closed source. You can't download it from anywhere. They'll install it on their system at some point in time, and you hope that it works. So that is the kind of way things are moving right now. So it's a fairly hard learning curve. So you try something, you mess it up, then you try to fix it. So that's how we are going about it. But we have been able to make progress thanks to our friends in the community. So hopefully we'll be able to make much better progress on this going forward. Go ahead.
So bandwidth numbers are where you can really tell that we're definitely utilizing the interconnect to basically its full potential. As you can see, we're getting about 23,000 megabytes per second, and these are 200 gigabit per second interconnects. So that's pretty much peak bandwidth right there. And MVAPICH2 is able to achieve that out of the box with the OFI provider. And bidirectional bandwidth, again, you're seeing 42,000, which is what we'd expect. So then, like I mentioned, we've also been able to extend support for the OPX provider. And so this is just a performance comparison between the 3.0 alpha version with the OPX OFI provider compared to the 237, which had support for PSM2, which is the older version of support for that same hardware. So these are, both sets of numbers here are taken on Intel Skylake CPUs with 100 gigabit per second OmniPath adapters. And as you can see, we're seeing pretty significant improvements in message rate and pretty much across the board here.
So these numbers are kind of in line with what Dennis presented in the morning. So as Dennis mentioned that they are currently primarily focusing on the small message range. The large message like enhancements are in the works and will be upstream soon. So those are the kind of like if you look at the trends, if you see that in the smaller message range, the gray bar is doing much better than the orange bar. So like 1.08 versus 1.22. So that is the optimizations that Dennis had referred to in the morning that the OFI provider has as opposed to the PSM. And this kind of gets reflected on the message rate side as well in a significant way, where we see that the OFI provider is able to significantly outperform the older PSM2 based provider. Once the improvements for the larger message sizes are kind of upstream, we'll do the evaluation there. So at that point, we believe that the large message performance would hopefully beat what the earlier PSM interface is offering. So again, Dennis, feel free to jump in if you have any other comments.
No, I mean, you pretty much covered everything. That's early numbers and more to come. So,
Yeah.
Yeah. Thanks.
So good stuff to come.
Nowhere to go but up. All right, so I think Hari's going to hop in and talk about the advanced versions of our open source software stack. But before then, anyone have any other questions on the open source version?
So like oh, sorry, Dongla has a comment.
Yes.
Dongla, can you just use the mic?
Can you go back one slide?
Can you go back one slide?
Oh, yeah.
What happened on the two opera for the orange peak? Any explanation?
Oh, are you the peak here?
Yeah.
That's a great question. That's probably either a tuning issue or just.
So that's probably the eager threshold. So typically for modern systems, the internode eager threshold is somewhere between 16 kilobytes to 30 kilobytes. So on this system, probably the eager threshold needs to be tuned. So that's probably
Okay,
what
so it's basically a tuning thing.
probably, yeah, that's what we believe. So this is probably a tuning issue.
Okay.
These trends are very commonly seen when you are switching to a different protocol before its time is due.
Okay, thanks.
Right. So that's probably where we switch from, like you said, eager. So we switch from PIO to SDMA.
Yes, right.
And then it'll
Yeah.
be,
Right.
eager receive on the other side.
Right. Okay. Hey.
Yeah, hey, somebody put a broken mic by me, so I think that was on purpose.
No, come on.
So one question on the Cray, you mentioned the slingshot.
Yeah.
You said that progress is slower than it could be there because I guess the software is open source. Did they give you indication that that's going to get better?
We have no clue. So we periodically do LL on /OFI, like their install. If the date has changed, we like try things again. So we have no lines of communication open between us and HPE. And as Livermore, as the guys with the money, if you can push for us, that will be helpful.
Okay, yeah, I'll get in touch with you about that. I don't know if we can do anything, but it'd be good to figure that out. And then one question on the process binding. So I work on some projects where there's the MPI application that would be running using all the cores, but then, oh, thanks. But there are also some services that would run on the compute nodes that we'd like to use cores that are different than the application cores. Have you had other people request something similar? We kind of want to stay away from the application cores so we're not interfering with it because these are background processes that are running.
So we have not had guys like folks requesting for that, but we have some. So for instance, MVAPICH2 has this optimized asynchronous progress thread. So we try to bind that to a separate core which is not being used by the application. So we have the ability to do that. One thing that can be done is, let's say, if these threads are supposed to be one per process, or let's say if these additional ones are they services which are supposed to be one per node, or are they supposed to be one per process? So could you give us some hints as to that?
Probably one per node would be sufficient.
Okay.
Yeah.
So we need to come up with some sort of a standardized method, like in which, so one simple thing we can do is we can ask the MPI library to reserve certain cores, saying that, hey, please reserve 1 core or 2 core or 3 cores, like per node. So if we do that, then we can try to work with the launcher to lay out the processes appropriately. I think that's one thing that can be done. But this is the first time we are getting this request. But yes, it can be done. Again, Nat, please correct me if I'm wrong.
I would agree. For starters, right, as a developer, you could do that with the manual core mapping, but that is kind of a pain to do every time. But yeah, like Hari said, probably the best way to approach that would be to have some kind of awareness for like what cores you want reserved, and then have the launcher set that up at startup. Or if they're like something that always runs on the system, the launcher could again detect, you know, in-use cores and steer the CPU binding away from it.
Okay, all right, thanks, guys.
And the enhanced launcher support that we were talking about in the original slide is we are trying to bring in Avalanche. Remember what we had done. So again, he'll be bugging you about that in some time. Arpan, you had a question?
Yes, thank you. So for asynchronous progress, what do you think? Shall we have one core for all the processes on the node? Will it give the best performance, or having one thread per process?
So go ahead.
Yeah. So which will give the best performance? Let's say like you have all reduce, I all reduce, okay?
So we have done research on both. So we had a functional partitioning based approach where we reserved one core, and that core was progressing communication on behalf of all the other processes on the system. That, in my opinion, is fantastic, because now that process can control congestion. So if, let's say from the point of view of congestion, if you're talking about it, suppose you're doing an all-to-all. If everybody is pushing messages at the same time, then that's really a waste of resources. You are in effect serializing it. So if you can have one process orchestrating communication on behalf of all the other processes, that'll be fantastic. Now, if you go back to the talk that Rich Graham from Nvidia presented, he talked about something called Gvmi, and that's something that like Kaushik is working on. So if we can do that, then we can have proxy cores on the Bluefield devices trying to progress communication on behalf of all the application cores. So that would bring a lot of control into how we utilize the network, how we inject traffic into the network. In the absence of, but the thing is, if you want one process to do progress on the others, there needs to be a lot of other things like to be in place. So there needs to be some sort of methodology to move data from the other process domain to this progress process domain. So that's a lot of additional work. If that is not feasible due to one of many issues, you could go the thread route. But with the thread route, the challenge is, how do you intelligently invoke the thread? So for instance, if you use up one extra thread for one extra compute core for the threads, then obviously you are going to use up a lot of cores. So how do you intelligently use it? Then that's what MVAPICH2 does. I hope that answers the question.
Yeah, thank you.
And just to add on to that, I believe even with the one process progressing all communications, we've seen a jump up to as much as 80% or higher overlap for dense communications, like I all to all.
Any other questions?
I have a question with regards to Sharp. So is Sharp supported with automatic hardware detection?
In automatic hardware detection, no, you have to you have to configure for Sharp and then enable it.
And does Sharp differ much from DPU, and in what way?
Yes, Sharp differs from DPU I mean, first of all, it's in the base open source MVAPICH2 library. And second, it's implemented for several different collectives, and it's implemented for both blocking and non-blocking collectives. And I think you might have to ask Hari for more of the implementation.
So basically, Sharp offloads your communication to the network. So it is a switch that is going to progress the communication for you. In the DPU, it is the network card that is going to progress the communication. So fundamentally, that is the difference. So Sharp has the potential to give you much better performance because of the way the communication gets orchestrated. Okay, but again, the number of things that you can do with Sharp is limited because it is on a separate device and there is no permission for you to touch that. DPU, on the other hand, you have all the flexibility. Okay, you can do whatever you want there.
So you could use both DPU and Sharp simultaneously?
Yes, you can. If you want to, yes, you can. But the question is, why would you need it? So Sharp will typically outperform a DPU if that functionality is implemented there. So why can't the process directly offload to Sharp? Why does it have to go to the DPU and then DPU to Sharp? So that's the question. Technically, yes, but practically, why would you want to do it? If something is there in Sharp, then probably offload it to Sharp. The other option is the switches have limited resources. So once you realize that you have hit the limit on the switch, then maybe you can have the DPU solution so that maybe the first 3 communications go over Sharp and the next 3 go over the DPU and something like that. So these are like options available. I hope that answers the question.
It does, thank you.
Yes, Moshe?
Yeah, so you mentioned, I think on the slides, that you offloaded to Sharp, scatter-v as well as all-reduce.
Yes.
Scatter and all-reduce. So scatter is actually offloaded to DPU, not to switches, right?
So Sharp technically gives us, again, Bharat, you can correct me if I'm wrong. Sharp gives us a couple of primitives, like it gives us all-reduce, and I think it gives us barrier as well. So what we did was we used the all-reduce primitive to implement a few other collectives. We used the all-reduce to implement like a broadcast, a reduce, where you could ignore some data. Okay, so for instance, if you call an all-reduce, where only the root puts in data, everybody else puts in 0, and the operation is sum. That is, in a sense, a broadcast. So you can use a particular collective operation. So again, Adam would know this much better than me. So Adam would say that, hey, you give me a scan, I can implement any collective. And he got a best paper for that.
So you did that for scatter-v?
Yes, yes. So basically, we were using the same primitive to, like in a smart way, to implement other collective operations. Any other questions? Okay, cool. So I'll try to run a little, and so that I don't stand between you and coffee, which is some place that nobody really wants to be, to stand between a person and food. Okay. So we'll talk about the advanced features in MVAPICH2X. So we have like 2 optimized solutions, one for like host-based communication that is called MVAPICH2X, the other for GPU-based communication called MVAPICH2 GDR. Okay, so this is a table showing why you should use MVAPICH2X compared to MVAPICH2. I will not belabor going over each one of these points, so please take a look at this. It's available on our website. So long story short, MVAPICH2X has all of these nice features. So one is it has support for optimized transport protocols. This is especially critical if you have dense collective communication, like intranode optimized kernel-based communication with CMA as well as XPMEM, and optimized asynchronous progress. So at a high level, these are the features that MVAPICH2X offers. And this is the kind of benefit that you get. So Moshe was referring to, let's say, Nic level congestion that can happen previously in his talk, right? So the QP cache thrashing and things like that. So if you are using like a connection-oriented protocol like the reliable transport protocol like RC versus the direct connect transport protocol, this is the kind of impact that they have with dense collective communication. So this is an example of an application called Neuron, which is like a brain simulation application. This is heavily used by the EPFL folks in Zurich. So we worked with them to see if we can improve the performance of the simulation, and by using optimal transport protocols, we were able to significantly improve the overall communication performance, especially for dense collectives. Okay. So this is the kind of benefits that MVAPICH2X can offer you, or rather the optimal selection of a transport protocol can offer if you are able to choose it. Okay. So similarly, we have support for kernel-based collective operations. So Linux has some support. So one is called CMA, which is available by default in the Linux kernel. So we were able to use it at a collective level to speed up certain collective operations like gather, scatter, broadcast, and the like. So this kind of shows the benefits of the asynchronous progress design. So as I mentioned earlier, if you have a thread-based design for making progress, the thread will have to be active all the time. That is the common logic. But does the thread really need to be active if you have smart interconnects? So if you are doing the eager protocol as we discussed earlier, in most cases, your network adapter is smart enough to progress the communication. You don't need to have a separate progress thread running all the time. So can we intelligently find out when we need the progress thread to be active? That is only when we have a large message operation, like a rendezvous operation, where the process has to get involved. So if we can find out those phases and just enable the progress thread at that point in time, we will be able to get away with oversubscribing that core and running the application thread as well as the progress thread on the same core. Okay. So by doing this, we were able to show significant improvements for like very standard benchmarks like high performance LenPack, HPL, as well as like a fast Fourier, like a 3D fast Fourier transform, like P3D FFT. So we were able to show significant benefits for both of these by doing optimized asynchronous progress. Yes.
Are you going to have a presentation about the async?
Yes, we had a paper at Euro MPA a few years ago. I can go into more details if you are interested. Maybe we can talk over beer or later or over coffee. Any other questions? Okay. So while CMA is good, the problem is that you still have to go to the Linux kernel space to actually perform the operations. So that kind of limits the performance significantly. But with XPMEM, these operations can be performed at the user space itself. So this has the potential for much more improvements in performance. And we were able to create shared address-based like zero copy reduction collectives as well as other non-reduction collectives based on XPMEM. So this gives significantly improved performance over your regular host space shared memory communication. But the only flip side of it is you have to install this additional kernel module, which is a fairly big thing if you are like a supercomputing center. So you always look askance at all of these kernel modules that you have to install. But if you do, you can get significant improvements in performance there. And not only at the microbenchmark level, but also at the application level, for instance, like a mini AMR or like a CNTK, like a deep learning kind of an application. So let me quickly go to MVAPICH2 GDR, which is the optimized solution for device-based communication. So folks who are familiar with GDR will probably know what is happening in these slides. So what is the typical modus operandi if you want to use a GPU on a cluster? So what you would do is you would copy your data using CUDA memcopy or HIP memcopy or whatever from the host to the GPU, perform your compute, move it back to the CPU, and then move it to a remote host. Okay. So this is typically what you do, right? You do CUDA memcopy, then you do a send and a receive, and then you do CUDA memcopy back. So very straightforward. So it's very easy to do, but it is not good for performance. So why is it not good for performance? So it's primarily because this path that we highlighted is not as simple as it may seem. You have like 4 different protocols that you can use to move this data. And depending on the relative location of the GPU and the CPU, all of those may not be applicable. So overall, if you look at the number of combinations possible, it's almost close to 16 different combinations. So if you are a very smart application developer and you can do all of these things, you could do something like this. Okay, you could write like a very good memcopy operation and pipeline that with the internode transfer operation and ensure that you get good performance. Okay, so this will be fantastic for performance, but very poor for productivity. Okay, what we tried to do in our group was try to see if we can have the best of both worlds. Can we have high performance with high productivity? And that's what we refer to as the CUDA aware communication runtime, where the application only needs to do an MPI send and an MPI receive. And the communication library internally is going to take care of orchestrating the transfers from one device to the other with high performance and high productivity. Okay. And we have been working on this for the last 10 years, and we have worked with several HPC centers, national labs, for this. Like we have had an ongoing collaboration with Lawrence Livermore National Labs for the last several years on this front with Olga and Catherine. So our current solution supports the GPUs from Nvidia as well as AMD. We are looking at the Intel's GPUs, so that would be next on our line. And we have tried to optimize a lot of communication as well as other processing operations in the MPI runtime. So these are kind of the prerequisites, and these kind of keep changing over the years. We have these RPMs available for direct download from our website. They are freely available. They are also available through the SPAC package manager. We also support different networks. So we support Rocky V1 and V2. We obviously support InfiniBand, and we have a plan to support like other network vendors. So currently we are working with Broadcom to see if we can bring in support for GPUs there, as well as like Cornelis networks. So we will see how that proceeds. So you will see all of these solutions coming out from our group in the future. So this is again a laundry list of all the features that the last release has. So some of the, again, we have a huge list of tuning variables. I will not go over all of these things. We have a full list in the user guide. But let me go over some of the more interesting features and performance benefits. So this slide kind of shows at a high level the kind of improvements in performance that you can get if you use an appropriately tuned CUDA-aware communication runtime to move data from GPU on one node to a GPU on different nodes. So you get almost 10 times improvement, and the performance is very close to as if you were moving the data from host to host on modern systems. So these benefits also extend to the application level. This is a molecular dynamics application from the University of Michigan called HUMDI-Blue. We also have advanced support for data types, but more importantly, these are some of the more recent results that we have been trying to get. So we are trying to see how we can use the advanced capabilities of networks to offload the processing of data. So there's some work that Kaushik has been doing over the last couple of years. So can we use the network's capabilities to move data from, let's say, non-contiguous location to a non-contiguous location in remote memory? So that's basically what these slides show. So this is some work that Tsinghua has been working on over the last couple of years. So typically, if you look at modern GPU systems, they are extremely dense in terms of compute capabilities. You have a lot of GPUs stuffed into a system, okay? So you might have 4, 8, or 16 GPUs on a system. So that's a heck of a lot of compute. But if you look at the amount of communication bandwidth going outside from that node, so I just read one like a report from Lawrence Livermore like about 6 months ago. So their next generation systems, they are envisioning having one 400 Gbps link going out of the system, okay? So imagine having one 400 Gbps link going out of the system and maybe 4 or 8 GPUs. So that's a huge imbalance in intranode communication and internode communication capabilities, okay? So you are creating islands of computation. And in this scenario, if you want to scale up to hundreds or thousands of nodes or scale out to hundreds of nodes, then this becomes a significant issue. So can we use some of these additional compute capabilities to compress data unbeknown to the application inside the communication runtime, send it out and decompress it and give it back to the application? So this is what we are trying to do with on-the-fly compression. And through these solutions, and this is again publicly available through the open source, through the released versions of the MVAPICH2 GDR runtime. So, and again, these are the environment variables. So these are the benefits that you get at the end, at the application level. And these are not at the micro benchmark level, these are at the application level. So you see that at the application level, you can get 18 to 35% benefits in overall execution time, which is fairly significant, okay? So at the micro benchmark level, getting like 10, 20, 30% benefits is very simple. But getting the similar benefits at the application level is a really, really big deal, okay? So we have also tried to kind of get similar benefits at a collective level. So this is the work that so here we were focusing on mostly point-to-point operations for on-the-fly compression. Here we're looking at collectives, and we are trying to see if we can do a collective level compression and get benefits on top of that. Arpan, you had a question?
Yeah, so on the compression, are we wasting a lot of compute cycles in compressing the data and decompressing it? So
we are definitely using compute cycles, but the question is, would that be better spent idling because you are waiting for the data to arrive? So do you want the GPUs to be sitting idle doing nothing, or would you rather have it compute and let's say finish the overall application quicker?
So in some applications, we have asynchronous communication or the non-blocking communication.
Correct.
So for example, in deep learning, we mostly have asynchronous communication.
Correct.
So in that case, we will be using some of the compute, we will be taking away some of the compute power from the application.
Definitely, yes, that is definitely possible. Again, this is something that you need to evaluate. So the first two studies were done with point-to-point primitives with a traditional HPC application, and also this was done for the PSDNF, which is an HPC application, and deep speed, which is a deep learning application. So it would depend on the kind of application that you are running, and we should also see if the GPU's capabilities are completely being used up by the application. So modern GPUs are real beasts. So several times, and this is kind of evident with the recent developments from Nvidia, where they have been trying to come up with solutions like MPS, where one GPU can be partitioned into multiple instances, like MIG as well as MPS, where one GPU can be partitioned into multiple instances, okay? So it is highly possible that even though you're using non-blocking communication and trying to schedule application compute and GPU in the background, you are still not able to fully utilize the massive power of these beasts of GPUs like A100 or H100. So in that scenario, yes, this could still be feasible. But again, this is something that you have to evaluate on a per application and per use case basis. In some scenarios, yes, it may not be feasible. I agree.
Sorry, one more follow-up.
Sure.
So do you think DPUs can be helpful here?
DPUs can be helpful. So as we saw in the morning talk by Rich, they mentioned that DPUs have several programmable devices. So one of the programmable devices on the DPUs is for encryption and decryption. So similarly, if they can have, let's say, engines on the DPUs for compression and decompression at a hardware level, then yes, definitely, it can make a significant change. And that would be fantastic. If that can be done, that'll be fantastic. Yes.
Okay, thank you.
Sure. So let me run forward. Again, these are some of the small message performance on the DGX2 system, where we compare Nickel, which is the Nvidia's collective communication runtime, and MVAPICH2 GDR. So as you can see, we are able to outperform Nickel or be very close to it in most, if not all cases, for small as well as large messages. So here we have tried to show how we have optimized like all-to-all and all-to-all V communications at the microbenchmark level and as well as at the application level with the HEFFTE application. This is an application from the Oak Ridge National Lab. So we are working with Alan there, Dr. Alan Ayala. I believe he's here at MUG and at least virtually, and you should be able to discuss with him. So those were on the Nvidia GPUs. This is on the AMD's GPUs with the ROCm-aware MVAPICH2 GDR. So here also we have optimized various intranode and internode communication for point-to-point operations as well as collective. So Kauthar sitting at the back is the person mostly leading this work. And the work on the collectives optimization here is done by Chen Chun, sitting back there. So again, as I said, I just come here and talk. The actual work is done by a bunch of other folks sitting behind. So this is the performance results we have with MVAPICH2 GDR on Slingshot, and this is again something that Kauthar is working on. So we are able to show very good performance compared to the other MPI stacks for like intranode as well as internode, point-to-point, and collective operations. So we have also done a lot of application level tuning, and we have a list of best practices as to how one can run, how best one can run an application on a cluster. So this is not just work done by us, there's also work like information contributed by a lot of people in the community. So again, all of these are on our website. I'll go over a couple of them. So as we saw earlier, the point at which you switch from the eager protocol to the rendezvous protocol has a lot of impact on performance because of the additional asynchronous progress that eager protocols offer over rendezvous. So by switching over to the eager protocol, we can get improvements in application performance for applications like Amber as well as Mini AMR. As we saw earlier, by using the correct transport protocol for certain applications like Neuron and SMG 2000, we can significantly improve the overall application execution time by saving on QP cache thrashing. Okay, so just like you have cache thrashing on the host side with L2 and L3 caches, you have similar issues happening on this network adapters as well. And by using appropriate transport protocols, you can significantly improve your overall application's performance, especially if you have dense communications like all-to-all or all-to-all V. So that is what these two slides show. And having the right collective algorithm selected for the right message size and the right system size and the right layout is critical. And that is what this slide highlights. So we in the group carry out significant tuning of collective operations for various clusters, and like mostly all the graduate students would hate this work, but at the end of the day, making sure that the right collective is chosen has a significant impact. Going forward, we are trying to come up with an automated framework where the library itself is able to intelligently choose what collective operation to use based on online performance analysis and evaluation. So you would be seeing this in future release of the MVAPICH2 runtime. So these kind of indicate the benefits that you get with the GDR software package. So we have a couple of new things that are coming up. So we have a Java bindings solution, MVAPICH2J. This project is primarily being led by Dr. Amir Shafi, who was kind enough to introduce us. So he'll be talking about Amir and Navras. Navras is sitting somewhere here, or maybe he's outside doing actual work. So they would be talking about the MVAPICH2J Java bindings package soon. So we released this earlier this month. So we'll have a talk on this in MUG later this week. So yesterday we also released a new version of OSU microbenchmarks with support for Java-based point-to-point and collective benchmarks, as well as Python-based point-to-point and collective benchmarks. So now you can use the same like semantics as the C-based benchmarks offer for Java as well as Python applications. So this is like a list of things that we want to do in the future. I would not spend too much time on this because Dr. Panda is going to discuss more about this tomorrow. So again, this is a list of acknowledgements, but more importantly, these are all of our heroes. So as I mentioned, every single slide that you saw here is work done by students and staff members. So we always give a shout out to all of them, present and past. And some of them, like Adam, have been kind enough to collaborate with us over the last 20 years and continually give us performance improvements and feedbacks and say, hey, you're not doing that right. You can fix that. And that has led to a lot of designs and papers, and we really would like to appreciate all of them. So with that, I come to the end of this talk. Thank you for your kind listening. And if you have any questions,